Question: what is a correspondence? What is a correspondence, guys? Or how do you use correspond or correspondence in a sentence? Or how do you define or describe correspondence based from your own knowledge without searching the Google or looking at the dictionary? Okay? On your own idea, what is a correspondence? A connection. What else? Equivalence. Relation. What else? Similarity. Matching. What else? Mapping. Pairing. Association. Comparison. Any other ideas? Any other word of comparison for correspondence? Response. Partner or company. And maybe you can still find other words that would compare correspondence. Actually, you're correct. When you say correspondence, it is a close similarity, a close connection, a close relation, association, equivalence, etc. Everything that you mentioned here are correct comparison or association to correspondence. Example of correspondence. For example, every item for sale in a store has a corresponding price. So an item is associated with price. Another example, every student in DLSU has a corresponding ID number. Okay, a student is associated with ID number. Every person has a corresponding age. So a person is associated with age. Every employee has a corresponding salary or compensation. So an employee is associated with salary. Can you give another example of correspondence in this way? Okay, that's right. Every car has a corresponding plate number. Every car has a corresponding plate number, unless the car is not registered in LTFRB or LTO. But if we are talking about legality here, so every car must have a plate number. So a car is associated with plate number. So there are still many examples of correspondence where one thing is associated with the other thing. Okay, and that kind of association is called correspondence. Why I am asking about corresponding or correspondence, it is because the idea of correspondence plays a central role in the concept of a function. Okay, I would like to write that one. Okay, again, the idea of correspondence plays a central role in the concept of a function, because our main topic for today or for this session is about a function. And what is a function as defined or considered in mathematics? Okay, so again, when you say correspondence is about relation, it's about pairing. Okay, for example, as what I mentioned a while ago, an item is associated with price, person with age, student with ID number, etc. Okay, so if you try to consider this one, it looks like we are putting it in an ordered pair. Okay, because in mathematics we consider a function as a special form of an ordered pair. But before that, let's have a glimpse first about a relation. Okay, in mathematics we also tackle a relation, but what is a relation? In mathematics, a relation is a set of ordered pairs. For example, we have this R1 set of ordered pairs where the elements are AB, ordered pair DE, TM, PQ. Okay, this is an example of a relation. Another example, if we have this form, okay, this is another example of a relation, which is a set of ordered pairs. So again, a function is a special case of a relation, meaning every function or all functions are relations, but not all relations are functions. Okay, so a function is just a subset of relations. But how do we define a function? Okay, let's have a formal definition of a function. So a function is a mapping or a rule that produces a relation or correspondence between two sets of elements such that each element of the first set is associated to exactly one element of the second set. We call it a mapping because we are talking about two sets here. Two sets. Okay? And then it is a rule because it could be violated to make it not a function. Okay? Or this rule must not be followed, and if that rule is not followed, then that particular thing, that particular entity is not a function. Okay? And that rule, that mapping produces a relation or correspondence between two sets of elements, and then with this characteristic. The first set is called the domain of the function. The set of all corresponding elements in the second set is called the range, and the set of all elements in the second set is called codomain. So there is an emphasis here of the corresponding elements that would take that would tackle about the range, and the set of all elements not necessarily has a correspondence with the first element, and that set is called the codomain. So if we use a mapping, if this is X, let's call it X the first set and Y the second set, all the elements here, the set of the elements in X is domain, and here where we can find the elements that would comprise the range, and every element there, the set of every element there is codomain. Okay, but not all elements in codomain is in range, but every element in range is also in codomain. So basically, range is just a subset of codomain. Let's have an example. So if we have this mapping, this is X, this is Y. If this is X sub 1, X sub 2, X sub 3, Y sub 1, Y sub 2, Y sub 3. If X sub 1 is mapped to Y sub 1, X sub 2 is mapped to Y sub 2, and X sub 3 is mapped to Y sub 3, this X sub 1, this set of X sub 1, X sub 2, X sub 3 is what comprise the domain, and the Y sub 1, the set of Y sub 1, Y sub 2, and Y sub 3 is our range. At the same time, this is also our codomain, Y sub 1, Y sub 2, Y sub 3. Okay, this one is a function. Why? Because each element of the first set has association in the second set. So x1 is associated with y sub 1, x sub 2 is associated with y sub 2, and x sub 3 is associated with y sub 3. And each element of the first set is associated to exactly one element in the second set. So x sub 1 is just associated to exactly y sub 1. X sub 2 is associated to y sub 2 only, and x sub 3 is associated to y sub 3. Because this rule does not violate the definition, then this makes it a function. This example makes it a function. Now you can also have this case. So another example, x sub 1, x sub 2, x sub 3, y sub 1, y sub 2, y sub 3, then we have y sub 4. X sub 1 is mapped to y sub 1, x sub 2 is mapped to y sub 3, x sub 3 is mapped to y sub 2. So what is our domain here? Still the elements x sub 1, x sub 2, and x sub 3. And our range, the corresponding elements of our domain, which is y sub 1, y sub 2, and y sub 3. As you can see, there is another element in y, but it is not associated. There is no association from an element in x, but still that's part of y. And if we include that to the list in the set, which is y sub 1, y sub 2, y sub 3, and y sub 4, that comprise our codomain. So again, the range is just a subset of codomain. Now this is still a function because it doesn't violate the definition. Okay, although y sub 4 has no association from x, from an element in x, but the definition only says that each element in the first set is associated. Okay, it did not say that each element in the second set must have an association from the first set. Okay, so it doesn't violate the definition. In that case, we emphasize two important characteristics of functions. these two important characteristics are just based in the definition of a function. One characteristic is that every element of the first set is associated to element in the second set. That is the first characteristic. For example, in our first example, every element in X, which is X sub 1, X sub 2, and X sub 3, is associated to element or to element in Y. Okay, X sub 1 to Y sub 1, X sub 2 to Y sub 2, X sub 3 to Y sub 3. Next important characteristic, the association is unique. The association is unique. For example, X sub 1 is associated only to Y sub 1. Okay? It's not associated to Y sub 2 to Y sub 3 at the same time. X sub 2 is associated to Y sub 2. It's not associated to Y sub 1 and Y sub 3 at the same time. Same goes with X sub 3. Okay? So these two characteristics are very important in identifying whether a relation is a function or not. Okay? For example, this one. We have A, B, C, D, M, P, Q, R, T. Suppose A is associated to M, B is associated to P, C is associated to P, and D is associated to R. In this case, let's try to check. Every element of the first set is associated to element in the second set. So as you can see, all elements A, B, C, and D have association to elements in Y. Now, is the association unique? Now, let's try to check. A is associated to M, and that's unique. Okay? B is associated to P. P only. And C is associated to P. Okay, that's also unique. And D is associated to R. So therefore, this example here is a function. Again, when you try to check the function, consider the elements of X and check the characteristics. Okay, so what is our domain here? Our domain is a set of A, B, C, and D. Then our range is the corresponding elements M, P, and R. But our codomain are all elements in Y, which is M, P, Q, R, T. How about this example? X, Y. How about this example? A, B, C, D, M, P, Q, R. A is associated to M, B is associated to M, C is associated to M, and D is associated to M. Is this a function? No. Why? Because the association is not unique. Again, consider the first set. Consider first the first set, the set X. Are all elements have association to elements in Y? The answer is yes. Okay? So we don't have problem with the first characteristic. The second characteristic is the association unique. So try to check A. Is A associated to only one element in Y? The answer is yes, it's M. How about B? Is it associated to exactly one element in Y? The answer is yes, and that's M. C, okay, and D, same goes with C and D. So therefore, this is a function. Okay, that function is called many to one, but we can explain that one further. So we haven't violated the two characteristics. Okay, every element has association, and then the association is unique. So that is a function. Again, the domain is the set of elements A, B, C, and D. Then the range is M only, but the codomain is M, P, Q, R. M, P, Q, and R. Okay? So that makes it the difference. Now, another example. This is set X. This is set Y. We have A, B, C. Then we have P, Q, R, S. A is associated to P. B is associated to Q. B is associated to S. And C is associated to R. Okay. Is this a function? That's right. This is not a function. Why? If you try to consider element B in X, it is associated to Q. At the same time, it is associated to S. So this B associated to Q and B associated to S makes it not a function. It violates the second characteristics. Violates the second characteristic or rule. The second rule of a function. So this is not a function. How about this one? A, B, C, P, Q, R, S. A is associated to R. B is associated to P. Is this a function? That's right. Okay, this is not a function. Why? The element C here has no association. So it violates the first rule or the first characteristics. Violate the first rule or the first characteristics. So basically guys, the idea of a function can be related. Okay, we can make an analogy on the relationship of biological mothers and kids. Okay, let's make an analogy for a better understanding of a function. Biological mothers and kids. Example, we have this set, the first set. The first set, we have set of kids, and this is set of ladies. So we have kid 1, kid 2, kid 3. And then we have lady 1, lady 2, lady 3, lady 4. Okay. Every kid has a biological mother. That's obvious. So we can have kid 1 is a son or daughter of lady 1. Kid 2 is a son or daughter of lady 2. Kid 3 is a son or daughter of lady 4. Okay? But not all ladies must have a kid. So that's fine. But all kids must have mother. Okay? Must have a mother. Every kid must have a mother. So this analogy makes it an idea of a function. However, if we have, say, kid 1, kid 2, kid 3, L1, L2, L3, L4, kid 1 is associated to L1 and kid 2 is associated to L2, and that's all, then this is not a function. Why? Because there is one kid here not associated to a mother. So it is impossible that there is a kid without a biological mother. No. A surrogate mother or a surrogate kid still has a mother through an advancement of science or technology, but still you get a cell or something from a guy and a lady, and you combine them, although it's not born naturally or normally the way most all kids are born. Okay, but still no kids don't have biological parents or biological mother, for example. Okay, now, so this is not a function. Now if we have kid 1, kid 2, kid 3, then we have L1, L2, L3, L4. If we have kid 1 is a son or daughter of L2, then kid 1 is also a son or daughter of L2. So something like that. This is not a function because it's impossible to have one kid with two biological mothers. Okay, so this is not a function. So basically, a function is like that. A relation of biological mothers and kids. So this kind of explanation of a function is through mapping. Okay, we are mapping one set to the other set. Okay, the mapping of the domain to the range. Okay, we can also define a function in a set form. So a function is a set of ordered pairs with the property that no two ordered pairs have the same first component and different second component. So this is the same definition with the one we had a while ago, but this one is in the form of ordered pairs. So example, if we have set T, this is 1 4, this is 2 3, this is 3 2, this is 4 3, and this is 5 4. This is a set of ordered pairs. So let's check if this is a function. Can you find two ordered pairs with the same first component and different second component? First, let's write the domain. The domain of this is 1 2 3 4 5. How about the range? The range is 2 3 and 4. This is also the codomain. Okay. So obviously this is a function because we cannot find two ordered pairs with the same first component and different second component. Actually, you can map this one, the one we did a while ago. Next, how about this set? 1 4 2 3 3 2 2 4 1 5. What is our domain here? Is 1 2 3. How about the range? The range is 2 3 4 5. Okay. This is the same with the codomain. Now, can you find two ordered pairs with the same first component and different second component? Yes, we have the 1 4 and the 1 5. Also, we have 2 3 and 2 4. So this 1 4 and 1 5 alone violates the second rule, or violate the condition that no two ordered pairs have the same first component and different second component. Okay, the one here is associated to 4, at the same time it is associated to 5. So this one here is a function, but the second example, is not a function. Question: is it clear? Next is functions defined by equations. functions defined by equations. So take note of the equations that we had discussed previously. Now, when we talk about equations and functions defined by equations, we usually associate this one to the discovery or the mathematics of René Descartes in the 16th or 17th century, I'm not sure, because of his studies on rectangular coordinate system, later on also considered Cartesian plane, okay, rectangular coordinate plane, rectangular coordinate system, or Cartesian plane. Because if you try to consider this rectangular coordinate system, this is composed of ordered pairs. So this one here, if this is x and this is y, this is x, this is y, this is another x, say this is x something, and this is y something, and a lot of them. Now, if you try to connect them, if you try to connect these 2 points with a line, so that makes it an equation. Or if you connect these points here, you take some points and you connect them, that would make it a graph or an equation. Okay. Now, later on, after 100 years, a function, the term function was coined by the German mathematician Wilhelm Gottfried Leibniz. Because basically the rectangular coordinate system became a very important concept in the discovery and the study of calculus, and Wilhelm Gottfried Leibniz focused most of his mathematics on calculus. Actually, he was considered, together with Isaac Newton, as the fathers of calculus. Okay, let's not talk about them. Let's talk about the function that they have discovered. Actually, again, Wilhelm Gottfried Leibniz coined the term function in 1694, according to historians, according to the history of mathematics. Then later on, in the 18th century, Leonhard Euler, another mathematician from Europe, Leonhard Euler, pronounced as Euler, stated that a function is a union or a combination of a constant and variable. Or variables. Okay. So these studies developed from there on to the modern times, but in the 19th century, a century after Leonhard Euler, a French mathematician, Peter Gustave Dirichlet, stated that a function is a statement of dependencies. A statement of dependencies. Okay? Meaning, one entity is independent of the other entity, and so on and so forth. So if we have, let's say, x and y, the value of y is dependent on x, or the value of x is dependent on y. However, in mathematics, for the sake of uniformity, we usually consider y is dependent on x. Or it can be written as y mathematically as a function of x. So we can have y is a function of x. So that's the idea, that's the statement from Dirichlet, that when you talk about a function, you talk about dependencies. For example, the salary of part-time employees depends on their hours of work. So if an employee is paid, say, 100 PHP per hour of work, and he works 5 hours per day, then his salary per day is is 5 times 100, which is 500 PHP. Or you can write this one as Y is the salary and X is the hours of work. So therefore, Y can be written as 100x, where X is the independent variable, and Y is the dependent variable. Because the salary only depends on the hours of work of a particular employee. So this one here can also be written as f of x, which is 100x. This is the salary, and this one here is the hours of work. And the 100 here is constant for a certain value for 1 hour. Okay, for 1 hour of work. So that's why f of x is equal to 100x. So that emphasis of idea is from Dirichlet, and that is actually very helpful in understanding functions and in dealing with functions. So functions defined by equations is more mathematical, more powerful, and more generalized form of defining a function compared to set of ordered pairs or tabular form. Why? It is because defining a function by displaying the rule of correspondence in a table or listing all the ordered pairs in the functions only works if the domain and range are finite sets. Okay? Although you can also write the functions in terms of a set given the ordered pairs. Okay, consider this equation. Consider y is equal to x squared plus 2x plus 1, where x is a real number. Okay, this one is a rule of correspondence. This is a rule of correspondence that is x squared plus 2x plus 1 corresponds to y. And this is a function because for every value of x, okay, for every value of x which is a real number, there is exactly one value of y. Okay, there is exactly one value of y. Say if x equals 1, which is a real number, y is equal to 1 squared plus 2 times 1 plus 1, which is 1 plus 2, that is 4. And 4 is also a real number. Okay, this is also a real number. Now if x is equal to, let's say, negative 5, if x is negative 5, then y is equal to negative 5 squared plus 2 times negative 5 plus 1. This is 25 minus 10 plus 1. That is 16. Okay? That is still a real number. So, for every value of x, for every real number you substitute to x, there is exactly one value. And that value is unique. So, therefore, this y is equal to x squared plus 2x plus 1 is a function. And again, your x is your independent variable and your y is your dependent variable. Okay? So, some equations are functions and some are not. Okay? Take note of that. Some equations are functions and some are not. So, example, if we have x plus y equals 1, then we have another one, y squared minus x squared equals 9. Then we have another one, y cubed minus x equals 1. Let's try to check which among these equations are functions and which are or is not. So we have solution. To find the function, to determine whether an equation is a function, let's solve for y. So first, for the x plus y equals 1. First, solve for y. So this one here, this x plus y equals 1, by applying the addition property of equality, we have y is equal to negative x plus 1. Note that this x minus 1 is a real number for each value. This is a real number for each value of x. For each value of x, which is also a real number. Okay? So therefore, and that value is unique for each value of x. So therefore, this one is a function. This one is a function. Okay? Now, for the second example, which is y squared minus x squared equals 9. If we solve the y, so we have y squared is equal to x squared plus 9. Then applying the square root property, we have y is equal to plus minus square root of x squared plus 9. Now suppose we have x equals 2. What will happen here? Y is equal to plus minus square root of 2 squared plus 9, which is plus minus 4 plus 9, that's 13, square root of 13. So meaning, for x equals 2, y, meaning, for x equals 2, y is equal to plus square root of 13, or y is equal to minus square root of 13. So we have two values. We have two values of y for one value of x. Okay? So therefore, this is not a function. Okay? It violates the second condition of the function, or the second rule, or the second characteristic. Now, for the third one, which is y cubed minus x equals 1, if you solve for y, this is y cubed equals x plus 1. Y is equal to cube root of x plus 1. Note that, I will write this one. Note that x plus 1 is a real number. Okay? Is a real number for every real number x. Okay? X plus 1 is a real number for every real number x. And each real number has only one cube root. So therefore, the association is unique. So therefore, this y cubed minus x equals 1 is a function. So in figure, in graph, or figure, we can have this one. Okay, we can have this one. Let's just have a figure of this. This example here is x plus 1 equals 1, and then that is a function. Okay, the other one, this is 1, the other one. Okay, later on we will just discuss how to graph a function, but for the sake of argument in this stage, we will just graph it for now. So we have, this is, okay, this one here is y squared minus x squared equals 9. Then for the third one, this is this one here is y cubed minus x equals 1. Okay, so these are the graph. Now, the best way of determining a graph, if it's a function or not, is through a vertical line test. What is a vertical line test? So, an equation defines a function if each vertical line in the rectangular coordinate system passes through at most one point on the graph of the equation. So, if any vertical line passes through two or more points on the graph of an equation, then the equation does not define a function. So, in the first example here, if we create vertical lines here, okay, whether how many vertical lines you draw on this graph, it only intersect to exactly one point of the graph of x plus y equals 1. So that makes it a function. However, in the second example, for example, this one here, just take this one here, this value of x creates two values of y. Okay, it intersects to 2 points in the graph. So therefore, this make it not a function. This one here is a function. This one here is not a function. In the third one, okay, whether how many vertical lines you create in the graph, it only intersects to exactly 1 point in the graph. So that makes this one here as a function. Okay, so that's the value of the vertical line test in determining whether an equation is a function or not through a graph. Now, take note that if a function is defined by an equation and the domain is not indicated, then we assume that the domain is the set of all real number replacements of the independent variable that produce real values for the dependent variable. Okay, it's better if I'm going to write that one. So note, okay, this is important note. This is very important note. If a function is defined by an equation and the domain is not indicated, then we assume that the domain is the set of all real number replacements of the independent variable. Okay, again, the independent variable is x that produce real values for the dependent variable, which is y. Now, the range is set of all values of the dependent variable corresponding to these domain values. So, take note of that. Now, if a function is defined by an equation, how do we find the domain of a function? Okay, so we have, let's change the color. We have finding the domain of a function if a function is defined by an equation. So for example, let y is equal to square root of x minus 4, where x is the independent variable. Where x is the independent variable. So solution. Okay. For y to be real, x minus 3 must be greater than or equal to 0. That is, x minus 3 is greater than or equal to 0, which implies that x must be greater than or equal to 3. So therefore, the domain is all values of x such that x is greater than or equal to 3. Or it can be written as in interval notation, which is 3 then positive infinity. Okay, so if you graph this one in real line, the domain is from, if this is 0, this is 3, from here to positive infinity. Another example, if we have, we'll say y is equal to 4x minus 1, where x is the independent variable. So we have solution. Take note that 4x minus 1 is real for any real value of x. For any real value of x. So therefore, the domain for this is all real numbers, or you can have this one is from negative infinity to positive infinity. Let's have another example. So if we have, say, y is equal to 2 over x minus 5. Take note that 2 over x minus 5 is undefined or does not exist if x is equal to 5. So therefore, the domain of the function y is equal to 2 over x minus 5 is all real number except 3. Or you can write this one, all real number except 3. How about y is equal to, example 4, x squared plus 3x minus 1. So this one here, the x squared plus 3x minus 1 exists, or gives a real value for every real value of x. So therefore, the domain here is all real numbers. Okay. How about example 5? Y is equal to square root of 25 minus x squared. Okay, so how do we solve this one? The domain of this function is the set of all real numbers. The set of all real numbers such that square root of 25 minus x squared is real number. So how do we do that? It only happens if 25 minus x squared is greater than or equal to 0. So how do we solve this one? Solving this inequality, 25 minus x squared greater than or equal to 0 is equivalent to 5 plus x, this is difference of two squares, times 5 minus x is greater than or equal to 0. Now, from our previous discussion on this topic, okay, remember, how do we find values of x for quadratic inequality? So, if we apply our previous knowledge on that, we can have our domain as all values of x such that x is between negative 5 and 5, or you can write this one in interval notation as negative 5, 5. Okay. So all the values of x, all real numbers from negative 5 to 5 is in the domain of this function, meaning all those values belong to the domain of this function, which is y is equal to square root of 25 minus x squared. Next, we have function notation. Okay, function notation, just to have uniformity in dealing with functions. We actually use f to denote a function, but we can also use any letters like G, H, R, T, and so on. But most often, we encounter, or you encounter, F to denote a function. So we can write, for example, if we have y is equal to x plus 1, we can write this one as a function of f such that y is equal to x plus 1. This form is called rule of correspondence. Okay. Actually, the term is not really important so long you understand the idea of a function. Or you can write this one as f such that all ordered pairs such that y is equal to x plus 1. Okay, this notation is the notation for the set of ordered pairs. Again, a function is a special case of ordered pairs. So if you write this one where you don't have to list all the ordered pairs because it is infinitely many, then you can write this one that the function is a set of ordered pairs such that the condition, meaning the given equation, y is equal to x plus 1. Or you can simply write this one as f of x is equal to x plus 1, because this is the usual function notation. Because take note that y is given by f of x. Remember the idea of Dirichlet that a function is a statement of dependencies where x is the independent variable and y is the dependent variable. So meaning y is dependent on the value of x, or the value of y is dependent on the value of x. So this is the notation. Y is equal to f of x. So therefore, y equals x plus 1 can be written as f of x is equal to x plus 1. It means simply that f of x represents the number in the range of the function of f. Okay, this is representation, the x here, representation of a number in the domain, and the f of x is a representation of the number in a range of the function. Okay, so these are the three notation, but mostly we will use f of x is equal to x plus 1 because aside from it is a simple notation, it is also widely used in mathematics, or mostly used in mathematics. So now, using this notation f of x equals y is equal to f of x, we are now ready to evaluate functions. Okay. Evaluating functions. So for y is equal to x plus 1, or f of x equals x plus 1, means f of 3, which is 3 plus 1 equals 4, means that f assigns the range value 4, to the domain value, the range value 4 to the domain value 3, or equivalently, the ordered pair 3, 4 belongs to f. Yan. So in evaluating functions, we just have to substitute the values of x to the equation to find the value of y, or to find the value of f of x. So example, if remember our equation a while ago, y is equal to 2 over x minus 5. So we can write this one as f of x equals 2 over x minus 5. Okay. Then you can also have, let's make it a. F of x is equal to 2 over x minus 5. Then let's say g of x for the second function, which is, remember, we have y is equal to x squared plus 3x minus 1. Then let's write h of x, which is the square root of 25 minus x squared. Take note also, we had a while ago that y is equal to square root of 25 minus x squared. So in evaluating function, you are just asked to find values of the function given the value of x. Example, for a, find f of 4. Say b, find g of negative 2. Then c, find h of 1. Or d, find g of 4 over f of 6. Okay. So how do you solve this one? Solution for a. So f of 4, meaning we are finding the f of x where x is equal to 4. So that is simply f of 4. Then substituting 4 to the variable x, we have 2 over 4 minus 5, which is 2 over negative 1 equals negative 2. So that's our f of 4. Then for letter b, our g of negative 2 is equal to negative 2 squared plus 3 times negative 2 minus 1, which is 4 minus 6 minus 1, that is negative 1. So 4 minus 6, that's negative 2, minus 1, that's negative 3. Yan. And then for letter C, h of 1, that is square root of 25 minus 1 squared, which is square root of 24. Or it can be written as 2 square root of 6. Now for letter D, we have g of 4 over f of 6. What is our g again? This one. Then our f is this one. So g of 4, meaning 4 squared plus 3 times 4 minus 1 over f of 6. Our f is 2 over x minus 5. So 2 over 6 minus 5. This is 16 plus 12 minus 1 over 2 over 1, which is 16 plus 12 minus 1, that's 16, plus 11, that's 27 over 2. So this is enough. So evaluating functions is just as simply as this, meaning you just have to substitute the given value to your independent variable, usually independent variable x. Questions so far? So another example, if let's say we have example f of x is equal to x squared. Okay, find f x plus h, and then b f of x plus h minus f of x over h, where h is not equal to 0. Okay. This one is the one that leads to the concept of limits in calculus. Okay, but we can also solve this one, meaning in evaluating functions, you don't just evaluate a number, okay, a real number. You can also evaluate letters. Example, this one, f of x equals x squared, then find f of x plus h. So solution, so f of x plus h, meaning you just substitute this x plus h on your variable. What is your variable? X squared. So x plus h squared, then simplify. So this is x squared plus 2hx plus h squared. So you're done. Then the second one for letter B, f of x plus h minus f of x over h. Take note, the f of x plus h is this one, okay, our letter A. So you can just write this one as x squared plus 2hx plus h squared. So x squared plus 2h plus h squared. Now take note, the f of x is our original function, this one. So meaning that is x squared over h. So x squared minus x squared, that's 0. So you remain here 2h plus h squared over h. Take note, you can factor out h. So we have h, then we have 2 plus h over h. Then you can cancel out h. So this is 2 plus h. And you're done. Question, guys, for evaluating functions? And questions for the functions so far based from our discussion, because we will still be leading or discussing more about functions, other types of functions and their graphs. Questions so far?